In today's meeting, I'm going to start with that perspective. I'm going to say, let's first of all do some thinking about this problem we're going to work on eventually with Easymax and in the pilot plant. And let's do all that before wetting any glassware or using any material or developing any sophisticated measurement techniques, or even taking any samples. So we're going to use a construct that we have inherited from Zenica, the original developers of DynoChem, called a process scheme. And I'm going to show you how to draw one of those and how it helps to make, as Peter Clark, my colleague, says, make the implicit explicit. So make obvious some of the things that maybe we would normally take slightly for granted about a process. And then, again, before doing any experiments, we'll use some of the tools in DynoChem to have a look at the equipment. I'm going to start actually with a 1 litre lab vessel, and then I'm going to look at a typical plant vessel, 1600 litre liquid volume, and then I'm going to look at an Easymax, 100 ml. So again here, without doing any experiments, we're going to get a very good visualization of the experiments that we may end up running, and also of the plant equipment or the pilot plant equipment into which we're going to transfer the process ultimately. And we're going to do one further step before going into the lab, and that is we're going to build what another of my colleagues, Wilfried Hoffmann, calls a visualization model. So we're going to build, assemble, and run a model based on what we currently know about our process. And that may not be very much, but we're still going to build a model, and again interact with that model to see what we can learn about how the process might behave under different conditions, what kind of profiles we might expect when we ultimately do run the process in the Easymax or in the plant. And that'll be an excellent starting point for when we eventually have some measurements. And then finally, step 4 in the workflow is, okay, let's do some experiments. Ideally, we'd already have some data, and that's often the case. You'll have some maybe relatively sparse experimental data about selectivities and yields and impurity profiles, which will mean that you don't have to necessarily do the experiments yet. But in this case, I'm going to assume that we're going to collect some experimental data. But having gone through the first 3 steps, we're going to know quite a lot in advance about those experiments, and they're going to be better experiments for that. Then we're going to take those experimental data and bring them into a DynoChem model. So actually the same model that we started with, the visualization model. That visualization model had some unknown parameters in it which we couldn't estimate without measured data. So we're going to estimate those using the fitting window in DynoChem, which is designed for doing just that. And in today's problem, we're going to need to get some chemical rate constants for reactions and some activation energies, which quantify the temperature dependence of the rate. At that point, we'll have run some experiments and done some thinking, and in a way, we'll have invested a fair amount in this problem. So we want to get some payback, use the tools, the knowledge we've assembled to answer some questions. So we're then going to run the model with the fitted parameters in another part of DynoChem called the optimizer, and we're going to find out the best conditions for running this reaction. And that's a really good indication of the next experiment that we should be looking to run to confirm the model and to tie off the experimental program, or potentially to go directly to scale up if we feel that we already have enough experimental data to support the model. And finally, we're going to then take this so-called optimum scenario, this optimized way of running the reaction, and scale it up. Still before doing any further experiments, and definitely before running in the plant, we're going to simulate the whole thing on the computer running at scale. And we're going to see in this kind of model-based process development approach, we're going to see potential issues, potential problems with selection of vessel or response of the control system or required jacket temperatures, issues like that that we'll never see in the lab. We can see them in the plant before actually getting there. And then potentially we will return to the lab for some final experimentation. So it is quite a different way, I would say, of working compared to a lot of what we see in the industry, where people's first response to any issue is to run some experiments, and sometimes to run a lot of experiments and then do some thinking at the end. Here we're trying to reverse that whole process and do the thinking up front so that we do fewer, more informative experiments.